penetrators, and Dr. Lee Magnus will give that presentation.
Yep. Okay. Thank you, Robin. Yeah, the first slide is the title slide. I'll be doing most of the presentation. We also have Dr. Kurt Lavender on the line from Battelle Pacific Northwest. He'll go into some of the details on some of the processing issues, and Brian Schuster should be joining me to talk about some of the environmental and toxicity issues we looked at with these tungsten heavy alloys. If you go to the next slide, just some of the background. If you're familiar with what the difference between depleted uranium and the other competing material that's out there right now for tank rounds and for kinetic energy rounds, it's basically the conventional tungsten heavy alloys, which are liquid phase sintered tungsten nickel iron or tungsten nickel cobalt alloys, and they basically fall short of the performance of depleted uranium by about 10% in penetration depth or 20% in terms of energy. It takes 20% more energy to get the same level of performance that you do with the DU projectile of an equal mass. The reason for that is shown in this slide. At the bottom center, I show a comparison of the penetration tunnels being made by equal mass, equal density, equal dimension DU and tungsten penetrators. So they both have a density of 18.6 grams per cc. And if you can see, the DU penetration tunnel is narrower but deeper, and that difference is especially obvious at the lower velocities, but it continues and basically reasserts itself later in the process at the higher velocities. The cartoon immediately above that sort of shows the illustration of what's happening. The conventional tungsten heavy alloys essentially are too stable under high rate plastic deformation. They build up and support a large mushroomed head. That's why they make a bigger diameter tunnel, whereas the depleted uranium projectiles very quickly go plastically unstable. They start softening with strain more rapidly than they are work hardening with strain. So that leads to a situation where any kind of stress concentration leads to a locally soft region, which is an adiabatic shear band. The material fails along that plane where the adiabatic shear band develops, so it discards deforming material more rapidly. It's sort of a resharpening kind of effect. It builds up a bit of a head, then discards it, and then builds up a bit of a head and discards it. So as a result, you end up with a very roughened penetration tunnel, but on the average much narrower than the tungsten heavy alloy tunnels.
So at the very highest velocity, 1700, they're pretty close. Is that what I'm reading from this?
Yeah, that's right. In terms of effective range on the target, though, the difference is still there. If you look at the velocity, measure horizontally on that axis, it's still about 100 meter per second shift between the performance of DU and tungsten, even at 1700 meters per second. What you're seeing really is at the higher velocities, the early part of the penetration process is essentially hydrodynamic. Inertial forces are dominating the flow and failure of both materials, and you really can't see any difference. The two penetration tunnels basically overlay for the first half of that penetration process. But late in the penetration process, as both cases, but the rods are eroding away, they're starting to slow down because the elastic waves can travel back and forth in that rod more and more quickly. So they both start rapidly slowing down, and then you start seeing the same behavior that you saw at the lower velocities the whole way down, that the DU tunnel is noticeably narrower. So it isn't a change in behavior, it's just that the relative importance of this adiabatic shear behavior versus this plastic mushrooming behavior changes with velocity. The other thing I'll point out on this chart is an instrumented mechanical test that you can see this behavior kicking in. If you do a dynamic compression test, now these were done with split Hopkinson bars, where you're crushing short L/D 1 or 1/2 cylinders of DU alloys in the case of the red and purple curve at the bottom, or tungsten heavy alloys in the case of the curves in the upper plot. And what you see there is that sudden drop in all the DU curves, that's occurring when an adiabatic shear band develops in that dynamic compression test. So the test is sort of being interrupted at that point by that plastic instability and localization, the adiabatic shear process, versus the tungsten heavy alloys. Again, they're stable during that whole deformation process, and the deformation, or the sample remains load bearing during the whole event. The axes on those plots are actually different. The DU ones go out to about 30% strain. The tungsten heavy alloy plots go out to about 100% strain. So the big difference in plastic stability and shear banding in an instrumented test. The next slide, which would be slide 3, shows why we were taking this approach with a nanocrystalline version of tungsten heavy alloys. In general, nanocrystalline versions of all materials tend to be stronger, tend to have less strain rate sensitivity, which is another thing that can tend to keep things plastically stable, and have less work hardening capacity because you've made them so much stronger. And so there's a lot of basic reasons why a nanocrystalline version of almost any metal is going to tend to become more and more plastically unstable. And the illustration is in that plot there for just iron, pure iron, as you go from a grain size of 20 microns for the lowest curves. So the curves here are both the quasi-static curve, which is the solid line, and then the dash curve is the dynamic, again in a dynamic compression test, the split Hopkinson bar. And so as you refine the grain size from 20 microns, the two lowest lines, to 1 micron, it jumps up. You see the strength has gone up a lot. And then as you continue to refine the grain size, the strength continues to go up, but the shear collapse, that shear band collapse, suddenly appears in the nanocrystalline iron. So in all these cases, they're all the same material, pure iron, but just through grain size refinement and the Hall-Petch relation, you're getting much stronger materials, but they're becoming plastically unstable. So that's sort of the basic approach we were trying to do with the tungsten heavy alloy, get that same sort of behavior either in pure tungsten or tungsten alloy or a tungsten heavy alloy, which is really a composite of tungsten and the matrix material. So we've been working that approach in some other areas, and I'll mention that a couple of times during the talk. But the approach we were looking at with Battelle was to look at some synthesis type processes. We looked at both a freeze-drying process and a glycine nitrate process, which is ultimately the one we spent the most time on. It looked like it had the most promise. Battelle had a lot of experience with that. They had patents on producing metal and ceramic powders using this glycine nitrate combustion synthesis process. And as we'll see, we have a patented application that came out of this work also for metals. So that's very quickly, that's a background in terms of why we were taking this approach, what we were trying to do with it. The next slide, just the technical objectives. When we started this project, there wasn't a real demonstration that we could get this behavior with a nanocrystalline tungsten-based material. So that was the first objective, was to demonstrate that yes, we can get the shear banding behavior and that penetration behavior by going to a nanocrystalline version of a tungsten-based material. Then we wanted to develop a process for making those materials in a cost-effective manner. And at the same time, and we'll get into it a little further in the talk, there were issues being raised with the conventional tungsten heavy alloys in terms of health hazard and possible carcinogen, mainly due to the nickel-based matrix that holds together these tungsten-based composite materials. So sort of concurrently with this test, we are looking at those issues and using the information from that to guide us in terms of what we select for the alloying additions or the matrix materials in our nanocrystalline composites. And then the last statement just said, one, there should be a cost saving life cycle wise by eliminating DU. And there's also the political issue with DU that at the time, again, when we started this project, DU production was scheduled to end in 2014. That's since been extended now to 2019, but that's a real issue for the Army. If they ever shut down the DU production lines in Aerojet's facility down in Jonesboro, Tennessee, they'll never get it open again because it immediately causes this, invokes this cleanup cost that has to be, the whole facility has to be cleaned, and they'll never go through the process again to create another dirty facility again. So that was one of the big impetuses pushing us to find an alternative to DU. The next slide.
Lee, what's the let's say environmental rationale for closing down DU production? Because I imagine there's big stockpiles of it.
Right. I mean, most of the raw materials, of course, are coming out of the nuclear industry. Originally, they used up a lot of the green salt. Now they're using a lot of the gas, hexafluoride gas. I mean, the whole rationale for not using DU, I think, is kind of weak, in terms of the actual science of why they want to move away from DU. It's mostly political. When they've done side-by-side tests with DU, actually DU is pretty safe. They've been tracking the guys from the first Gulf War. There was a lot of them that got fragged with friendly fire. So it was our DU ammunitions that were embedding frags in these guys, and there's really been no ill effects from that. And some of the rat studies and things like that they've done since then show that DU really isn't an issue. Some of the tungsten heavy alloys are actually worse, and Brian Schuster will go into more details about that. But again, coming mostly from the matrix alloy, not the tungsten phase itself. I don't know if I answered your question, but
yeah, that does. Thank you. I appreciate it.
Okay.
There's also been some toxicology and health physics reports done by the I think Marianne Parkhurst here at our lab did this for ARL many years ago, and again, the same conclusions were that the DU wasn't the health hazard as much as the perception.
So the next slide is one of the mandatory slides, also the technical approach. So we really had it broken down into 5 tasks. I'd say the first one was to make these nanocrystalline powder materials and to demonstrate this ballistic behavior. And we looked at a variety of different approaches, the glycine nitrate process, which we'll go into more detail, freeze drying, which is also a spray process where you dissolve metal salts, and a little bit into direct metal powder formulation, but primarily the first 2 approaches. And then task 2 was looking at how do we consolidate these materials. That's always been the big trick with these nanocrystalline materials, is producing a fully dense product without growing the grain size too much in the process. And again, remembering that slide about the nanocrystalline iron, it looked like around 250 nanometers is kind of the target goal, at least for iron, which is another BCC metal. we probably want to be in that same neighborhood with the tungsten-based materials. So getting to that ended up being our big problem in this project, was getting to that kind of grain size and full density was a real obstacle. And then the task 3 was just to optimize those processes. Ideally it was going to be in a phase of ballistic testing of different candidates, and then coming back to modifying the process and testing again. We never really got that far in the process. We did produce one sample that we did do some ballistic tests in task 4, and I'll show the data from that. But we really got stuck in task 2 is where we really ended up having a lot of trouble. And then task 5 is sort of overarching. It started right at the beginning and continued both literature survey, and then also Brian Schuster was doing a lot of other tests, looking at what the issue really was with these tungsten-based materials. He was working with the CHIPM and AFRI folks directly, looking at some of the same materials they were testing rats and other things with, and looking at some of the aerosols as well as trying to come up with a corrosion test, a method of assay to guide us, so we don't have to do, because rat studies are very expensive, but at least have a pre-screening test looking at corrosion aspects that could serve to guide our selection. Okay. Next slide. Just very quickly, there's sort of a flow chart of the two main approaches we looked at. On the left is the freeze-dry process, where you dissolve metal salts in a liquid, sublimate out the liquid, and then reduce it in a hydrogen-reducing atmosphere to produce the metal powders. The other approach we did was and was our main focus, was the glycine nitrate process, where again you dissolve the metals and the ammonium tungstate in a nitrate solution, which is heated until it dry it out and then combust it, again reducing it to the metal powders in the end. I don't know if Kirk has any other things to add to this at this point.
I think the only thing I would add is that the glycine is a pretty energetic event. So when this spontaneously combusts, that's what produces the fine particulate size. Is the high energy associated with the combustion, and so you end up with that's how you end up with the nanoscaled materials.
What kind of scales were you doing this
on? The scale we were doing it on for this work was like 75-gram metal equivalent batches.
So if you had to scale that up to a production level, and understanding that there's a fairly energetic event taking place, how would you imagine doing that?
Well, we've actually done it two ways. We've actually done it at the laboratory. We made a rotary kiln system where you introduced the solution and you poured the solution down a rotary kiln, and as the solution flowed down the kiln, it reached the combustion temperature and then combusted. And that was the sort of the Battelle approach to large-scale combustion synthesis. But when we licensed the process to Praxair, and they're no longer Praxair, they're I've drawn a blank on the name right now. They adapted it, and they ran a variant of the spray drying process with it. So they took the glycine nitrate process and converted it into a continuous spray drying sort of approach. It's very similar to spray drying, but it does go through the combustion. And so in their case, they're doing large quantities. This is a nearly continuous, kilogram per hour type process for producing fine ceramic powders.
Okay, thank you.
Mm-hmm.
Slide number 7 just couple of quick things on what we were going to, just more details on the technical approach, this ballistic test, just a schematic of showing how we do those kind of tests here at the lab. We do ballistic comparisons against actual RHA, rolled homogeneous armor plate. You see in the yellow box there the example of a laboratory sabot, so we can put the material in a launch package. It's pushed out of our lab gun through our experimental setup, which has X-ray equipment to measure velocity, to measure the pitch and yaw, because that can really push your numbers around. So you got to verify you have good pitch and yaw at impact, and then look at the residual velocity out the back, or how much penetration into steel that you actually have. The next slide shows what we were going to do. We have a large database for both conventional tungsten heavy alloys as well as DU alloys for a standard set of rods. These are all 65-gram mass rods. This particular plot is showing the data for L/D length to diameter ratio of 15. So the rods are 15 times the diameter in length. And on this plot, I'm plotting limit velocity, which is the velocity required to perforate this given target. In this case, it's a 3-inch plate of rolled homogeneous armor as a function of alloy density. So you're seeing, if you look at the line with the, let me see if I can get the pointer on here, the black line here with the black data points, those are all conventional tungsten heavy alloys. So as you go from an 80% tungsten nickel iron to a 90% to a 93 to a 97%, as you go up in density, the rod gets a little shorter, but it also shrinks in diameter, and the mass to presented area of that projectile shrinks down. So you see this general trend that the limit velocity, it takes less energy to get through this given plate, this 3-inch RHA plate with the higher density material, and that's your typical sort of trend line. Those are all mushrooming type tungsten heavy alloy materials like you're seeing in that little box there. Among the DU alloys, for the same density as the 97 tungsten, this is exactly a reflection of what you saw in those two penetration curves. Again, the limit velocity will drop 100 meters per second for the standard U3/4 tie alloy. And if you go to even higher hardness DU alloys, they develop that adiabatic shear failure even earlier, so less deformation, less mushrooming is required to discard that material, and that actually lowers the limit velocity another 50 meters per second or so. And we have a family of other different DU alloys down here on this plot. So the red lines are the shearing materials like DU. Pure tungsten are these blue data points that are up here. If you look at pure tungsten or similar kind of materials like tungsten tantalum, they're even more stable than the tungsten nickel iron materials. You see this extreme mushrooming behavior. So what you're seeing is it actually takes even more energy than a tungsten heavy alloy rod to get through the same target. The other thing I'd point out on here is we did have one early proof of principle with a nanocrystalline material that we did with Ardec and with NIST, mechanically milling. It was a relatively low density material, so we weren't quite sure we could attribute all that to the tungsten phase because there was a large volume percentage of matrix in that material. We were about 40% matrix at that point. But you can see its data point is very close to this DU performance line, not the tungsten heavy alloy line. So that was, sort of an indication that we should be able to get that behavior if we could get a whole tungsten heavy alloy to behave that way. Next slide. A couple of quick slides just on some of the background and the health effects with tungsten heavy alloy. Again, Brian Schuster will get into more detail with that, but this all came out of a study they did for the Gulf War illness things, looking at those DU frags. They were worried about the DU frags in the troops, and they decided to throw in as a comparison some conventional tungsten heavy alloy pellets as well. And what they found was after 2 years, The DU rats were fine, no ill effects at all. But after 6 months, all the rats that had been embedded with tungsten nickel cobalt, which is one of the major alloys that's out there, all of them had nasty tumors, had metastasized to the lungs, and they all had to be destroyed within 6 months. They were usually showing signs within 3 months. And when Brian looked at the pellets themselves, what he saw was, again, with tungsten heavy alloy, it's a composite of these tungsten particles embedded in a nickel, cobalt, tungsten matrix that, at least to a depth of 3 or 4 of these tungsten particles, depth-wise into the microstructure, that the matrix had been completely dissolved away. So all that, you basically put a galvanic cell, 2 dissimilar metals in a salt environment in the body, and that nickel cobalt matrix showed up in the bloodstream, in the urine, and was, nickel was a known carcinogen. The cobalt probably didn't help, but it certainly didn't help limit the amount of nickel that went into solution. So that was a surprise out of those tests initially.
So in those studies, they just put a piece of the alloy subcutaneous in the skin, or do they put it near an organ, or?
They embedded it in the rear muscles, in the rear legs.
Okay.
The rats. Yep. They had some they did with four little pellets, and some they had 20 pellets. So
it's
a large
kind of a
loading.
strange test. I mean, in one case it's becoming bioavailable, in the other case it's not.
Yeah, the other case is the tungsten nickel iron alloy. So there was some dissolution early, and again, Brian will go into more detail later. But what happened was essentially you ended up with this iron oxide coat that very quickly showed up on the pellets, and kind of shut off the diffusion process fairly early. So the nickel levels quickly dropped in the blood and urine samples, for example, in the rats. So and those rats survived the 2-year study. So it was kind of interesting that the nickel iron alloys, which are typically the older family of alloys, did not appear to be hazardous. So next slide is some of the other things that we were going to be doing, that collecting some aerosols, the respiratory health things. We did during some of our large caliber ballistic tests. We collected some of the aerosols. Brian worked with the University of Texas on doing some bioassay work on that, on cytotoxicity. And then the main thing he looked at was different families of tungsten heavy alloys with different ratios of tungsten, nickel, and iron and cobalt, and how much iron did you need in the system to make it protective of that corrosion and dissolution of the matrix. And he'll go into more details on that, but just to give you an idea of what the approach was going to be. I'm running a little late, so the next slide is, well, that's a residual. You can skip, you can save that one, skip 11. So on to the results with the nanocrystalline. This is mainly task 1, nanocrystalline powder production. Again, we looked at those 3 different powder synthesis approaches. Looked at our criteria were, how fine a grain size powders could we produce, how centrable were those materials, and how scalable was the process going to be. Eventually, we down selected to the glycine nitrate process because it did produce the finest tungsten crystallites, averaging around 30 nanometers, where they were like twice that size with the freeze-dried process. And we had reasonable success getting to, moderate densities in the early sintering process with that material. And as Kurt just explained, it's a very, it's a reasonably well scalable process to do production also. So we thought that was the best approach to take going forward. Next slide. There's just a schematic of, maybe Kurt, do you want to explain some of the stuff that's in the picture there, but again, a little synopsis of what you do in the glycine nitrate process in terms of putting the things in solution, then drying them to the point of the combustion. And here's an example of their facility here.
Right, and I think one of the things that the facility, when it does sort of coarse, I shouldn't say coarse, when it does ceramic powders, it can really run continuously, but the problem with the powder sizes that we're trying to get here is they're pretty difficult to handle, and so in this case, it's a batch system that they would have to scale to in order to capture that. So your production filter and your collector system, they can't be exposed to air. They have to be captured in a batch. That would be the only limitation, would be the batching of the capture system.
All right. Next slide is number 14. The photograph in the upper right is example of some of the powder being produced, and you see it's an agglomerated powder with very small individual crystallites of the tungsten in there, again with that about 30 nanometer grain size, and verified also with the XRF analysis. And the squared, the microstructure down at the bottom is an example of one of those early sintering trials. Again, not full density, but so there's a fair amount of residual porosity in this sample, but we had pretty good grain size, looked promising at this point, sub-micron finished grain size in the material. So the next slide.
I guess the only thing I might add on that one, Lee, back to the agglomerate size, is that our health physics people don't consider that a nano powder, and so some of the issues that you hear about handling nano powders, the agglomerate size that we work with is large enough that it's not considered a nano powder, even though it's nanocrystalline and nanostructured.
Okay. So next slide had to do with now working with these powders. We looked at a lot of different things, trying to consolidate these powders to full density or nearly full density, yet not grow the grain size. And probably I should ask Kirk to go over this in a little bit of detail. There's some slides that follow that show some examples of the stuff we did. But
yeah, if you want so there's a pretty well-known challenge in consolidating these nanostructured materials and maintaining the nanostructure. There's some basic physics that occurs with the contact angles of the particulate during sintering operations that ultimately limit what you can do. So in a lot of cases, you're required to use extremely high compaction pressures and to facilitate compaction of the powder prior to sintering it. And then what we tried to do with sintering aids then is sintering is controlled by surface diffusion between the particulate. And so we tried to add small amounts of elemental constituents in there to facilitate the diffusion without causing grain growth. So, and one of the best actors for that is nickel. So in some cases we used small additions of nickel to enhance the diffusion of the tungsten. And then we tried a series of things in sintering conditions, whether it was sort of soak times, heating rates, modified sintering atmospheres so that we could control the sintering because it's a diffusion control process, and there's even some vapor involved in that. And then what we found was during the sintering processes, we just could not get it to the high densities without in sintering, and we tried a variety of sintering aids and sintering things. So then we decided the only approach then was to incorporate pressure during our sintering cycle. So this is more like a hot pressing operation or a hot isostatic pressing. And these were things that done. Now ARL also worked with the powder quite a bit, and they have a very nice system for breaking up the agglomerate size, and so they also did some work in agglomerate size. And I think ultimately the process that produced the large pieces for ballistics testing were run through the process to reduce the agglomerate size and centered at ARL.
Right. Yep. All right. So the next few slides are just some examples of some of the things that we're going through. I mean, we don't have to go into it in too much detail, but looking at different lubricants and high pressure conditions in terms of powder compaction, trying to improve the centerability. That was slide 16. Slide 17 shows some of the results using grain boundary inhibitor, this yttria. And I guess the interesting thing there, and maybe Kurt can talk more about it, but during the glycine nitrate process, it seemed like the yttria got concentrated into certain areas, was not widely dispersed like we had hoped, so it wasn't very effective as a grain boundary inhibitor.
That's right. That's right. And if you notice those compositions, I don't remember, is there another slide of the shrinkage, or is this the main shrinkage diagram we have? So if you look on the slide, I think there's another slide coming up.
Right, this is the only one for the yttria, yeah.
Yeah, that's right, okay. Right.
Yeah, here's
okay, here we go.
One for the nickel. And, yeah, maybe you can do it in more detail.
Yeah, now this slide, so the light blue line is the centering shrinkage that you see with temperature for the tungsten only. And so you can see that we needed on the order of 20+% linear shrinkage for the green densities that we worked with. And if you look, so you can see that the tungsten only was requiring very, very high temperatures for centering shrinkage, at which point, because these powders are agglomerates, at this point then they would grow to the agglomerate size, so we'd get a lot of coarsening of the tungsten size. So we couldn't really maintain the tungsten particle size at density. So we knew we needed to add some type of a centering aid. So if you look on that graph, then there's a series of centering aids that are, and you'll notice that the more nickel we added, the higher the centerability. So the two lines on the left where we got a lot of shrinkage at very low temperatures were 3 and 0.5 weight percent nickel. Then we added lesser nickels, and then we tried some combinations of silver and copper because nickel causes some coarsening. So nickel causes some coarsening of the tungsten. So we tried some silver copper additions too to try to keep the actual grain size down. So this was the centering aid diagram and how they went.
Here's just an example with moly.
Yep.
We're probably running a little late. Maybe we'll try to move a little faster. But,
Okay.
Yeah. Again, this is examples with the 0.5% nickel. So this, let's see, where were we? Okay, this is basically one of the best microstructures I guess we got.
Right.
These were only in very small compacts, but we did get in the order of a 200 nanometer grain size in this case, but only in a small sample. So again, the trick is how do we make a bigger sample? And let's go to the next slide. Well, again, some other attempts with the pressure. The big thing, trying different consolidation swaging approach to try to, again, consolidate this material before we enter the sintering process, help things along. And then the other major work in terms of consolidation was looking at hot isostatic pressing. So again, the problem we were having with these highly agglomerated powders is that you end up with when you fill the can, you end up with a material with a very low tap density, so a lot of void space. And when you hip consolidate and the can crushes in, you end up with a highly deformed final can with very difficult to get useful specimens out of. So tried various things to try to improve that, but weren't very successful. I don't know if you have any other things to add to that, Kurt.
No, I don't. And that's been a there's a lot of promise in nanostructured materials, and this has been the consistent problem. We've struggled with this. This is a difficult area.
So here's where we started looking at some of the de-agglomeration process. This is the milled powders. So after going through the GNP process to produce, in this case we were looking at a tungsten nickel iron composite powder, was then wet milled to de-agglomerate the powders so we could improve the packing densities in these materials. And with some success. I mean, what you notice is normally you don't see the hardness going up at the higher sintering temperatures or higher hot isostatic pressing temperatures, but because basically these numbers here at 850 are low because there's still a fair amount of residual porosity in the material, but this is more closer to the true hardness of the material when we're getting closer to full density. So there was some promise there, but again, we had difficult times getting a large enough sample to work with. There was still a lot of shrinkage, and I know the Patel guys went through a lot of iterations trying to come up with a can that would consolidate and not burst open or
right.
Difficult thing to work with. Go to slide 27. Same thing. It's just comparing the milled and unmilled powders. So in the end, what we ended up doing was going with the ARL wet milling process to de-agglomerate, and then conventional sintering at the end. We were working with Brady Butler over in the materials division, and he was looking at tungsten rhenium alloys that were made by mechanical alloying kind of processes. So we wanted to look at a much more intimate mixture of the two materials by the glycine nitrate process. So that's what these powders were, and then they were de-agglomerated in Brady's wet mill and then sintered. And we got a pretty good material. It's just barely submicron in the end, but close to full density.
Are those black spots then not pores, or are they something else?
I think those are pullouts more than pores in the polishing.
What's a pullout? Oh, are you pulling out crystallites or?
Yeah.
Okay.
Yeah, the porosity wasn't that bad.
Okay.
Yeah. So this is the material we ended up making. We didn't have much material to work with, but we ended up making one ballistic penetrator. So we tried to make that shot count, and that's the result you're seeing here in the table here on slide 29. I don't know if you can see if the contrast is good enough. This is the projectile flying. We have two images here in the X-ray. You can see the pusher plate in the launch package here behind, and there's a plastic obturator you can maybe faintly see there. But you see it was a very good flyer. Our measure of the total pitch and yaw at impact was only less than half a degree. 0.43 is the number we came up with. So good impact. The velocity was close to where we wanted it. 1417. If it had gotten through at that point, we would have been sure that we'd had a material that was better than a conventional tungsten heavy alloy of the same density. This material was about 18.5, almost 18.6 in density. We did side-by-side comparison tests into the same block of RHA with a conventional tungsten heavy alloy here. This is the X9C alloy, which is 97% tungsten nickel iron, and its limit velocity is about 1420 meters per second against this target. So remember that a conventional tungsten heavy alloy would be, or a pure tungsten material would have been worse. Let me show I'll show that on the next slide. Again, here's the section target from that shot with the glycine nitrate processed tungsten rhenium. First thing you notice is the penetration tunnel is roughened. You can sort of see the roughened walls of the penetration tunnel, and there's lots of little chips of the material lining the tunnel. So if it had been a conventional, like if you make tungsten rhenium alloy in the conventional way with conventional grain sizes, you get a behavior that's like this. We haven't shot at tungsten 5% rhenium, but people have shot tungsten 26% rhenium and 10% rhenium, and they all behave basically like pure tungsten. Extremely stable mushrooming behavior. You end up with a very smooth penetration tunnel, being not this roughness that you're seeing on the walls, and it never really lets go of the material. The entire penetrator is still one piece essentially after the event. It's just been turned from a solid rod into a hollow tube. So we didn't have that happening here. We were definitely seeing some shear localization and discard behavior. I think that's why we're in the same neighborhood as the tungsten heavy alloys, which also display a little bit of this behavior with the tungsten nickel iron matrix. So we were getting a little bit of that behavior with essentially no matrix phase. It's just tungsten rhenium material. But again, that we're still way far short of DU performance at this point. Just to show where we are, the next plot, the data point, I mean, if I had to assign a limit velocity to that one shot, it was very close to getting through the target. So we were right on the edge. So it's basically on the conventional tungsten heavy alloy line. Like I say, if it had been a pure tungsten type material, it would have been above the line. So we were seeing some improvement, but not a very dramatic improvement, and well short of this gap of what you get with the U3/4 tie alloy. So that was basically the ballistic results. Now we have the section on all the health survey stuff. Brian is here. He can go over some of these slides unless there's some questions at this point.
So how much time do we have here? What are we doing?
About 10 minutes.
Okay. So I guess all of this stuff has been published, so I could make the manuscripts available. With Professor Murr at the University of Texas at El Paso, we did some tests where we examined the cytotoxicity of aerosols generated from the ballistic impact, sampled the size of the particles, and I guess there was a fairly dramatic effect, but I guess I'm not sure that was exactly the best screening method, because it could have been altered by the presence of some of the propellants in the test. I think what was more important, I have to figure out, okay, is the in vivo corrosion behavior. So this is something, it says it's listed as in preparation, but that has since been accepted for publication and is available. So I think Lee covered this before. You have this two-phase microstructure where you have pure tungsten particles that are surrounded by a matrix phase, and for the tungsten nickel cobalt alloy, the composition of this matrix phase is 43% by weight of tungsten, 38% by weight of nickel, and 19% by weight of cobalt. For the tungsten nickel iron, it's more like 22% by weight of tungsten, 51 nickel, and maybe 2% iron. And if you look at if you look at the concentrations of metals present in the urine of the rats taken at different time points, so 1, 3, and 6 months, you see an ever-increasing concentration of tungsten, nickel, and cobalt. And if you normalize that ratio, it matches that matrix exactly. And so it's pretty clear from that, plus some subsequent SEM analysis of the corroded pellets, that it was definitely coming from the matrix only. And in contrast, the tungsten nickel iron alloy had initially elevated levels of tungsten and nickel, and then that dropped off steadily dropped off steadily with time. And if we examine those pellets that were recovered from these tests in the electron microscope, you see the formation of this thick iron-based oxide that shuts down the operation of the galvanic cell. And so it makes the both tungsten and nickel limits the bioavailability. We did some work trying to adapt some sort of standard assays that were used for medical implants. We did some others just looking at the simple corrosion and analyzing what was coming out in solution in phosphate buffered saline. What we found with sort of the standard ASTM F2129 on tungsten heavy alloys, that doesn't seem to be a good screening test for those materials. That's meant to screen materials that are engineered to resist corrosion in the body. And so whether these alloys cause cancer or long-term health effects, they corrode either way. And so whether that corrosion is through galvanic cell corrosion or through passivation with the oxide formation, this just isn't an ideal screening method for that. So what I think was a much better screening was just simply doing long-term soak experiments in the phosphate buffered saline, and then examining the surface. And we started to identify a range of different nickel iron ratios that would behave similarly to the 7 nickel 3 iron, which was the alloy that did not show tumors when it was present as an embedded fragment. So that we examined what was coming out in solution with ICP OES, and then examined the surfaces with SEM, and then looked at the surface chemistry with XPS. I have a conference paper that we wrote on this, and so this shows the whole range of different alloy compositions that we looked at, including the baseline, which was the identical matrix composition to the tungsten nickel cobalt alloy. Moving on to slide 38. This shows some of the corroded samples where the what I'm calling the tungsten 2 nickel 1 cobalt shows just massive dissolution of that matrix phase, and in any of the other iron-based alloys, you did see evidence of formation of that passive iron oxide, and so that suggests that we can move away from the 7 nickel 3 iron alloy to some other combinations. And I guess this can be kind of a long story, but to make a long story short, there's evidence that you can improve the engineering properties, so the ductility and toughness of some of these alloys through reducing the nickel to iron ratio. Sorry, increasing the nickel to iron ratio. Moving on to 39, I can provide the conference proceedings if anybody is interested in. It's just looking at the ratios of all metals that are coming out in solution, looking at each individual species like the tungsten, the nickel, the iron, which is fairly easy to do in a controlled manner in these experiments that you wouldn't necessarily have the opportunity to do during an in vivo study. And so I think the main thing to take away from this is, in any case, the corrosion of the tungsten nickel cobalt alloys is associated with preferential anodic dissolution of the matrix phase, confirmed in a number of different cases. And you have a decreased dissolution rate in any of the tungsten nickel iron alloys. And there's some evidence that as you increase the iron concentrations, that you decrease the dissolution of nickel. And in some cases, though this is a little bit counterintuitive, you can increase the rate that the tungsten is dissolved. Although in this case, that may not be all that bad. The one thing that was shown in the Laurie Brazell study was that pure tungsten alone implanted in the rats wasn't associated with that same tumor formation. There were no adverse long-term effects. And in general, the amount of the oxide coverage on corroded surfaces increases with iron concentration. But I guess from this, you can actually pick out sort of a minimum threshold, so it's something that may require further examination. I think we can skip ahead to, I guess Lee has, starting on slide 42, the project funding.
Yep, this is just one of those, the mandatory slides again, the project funding and then some of the leverage funding. We were using some of our in-house funds. We were also working with the folks at RDEC with these materials. Also worked with Global Tungsten Products out of what used to be GT Sylvania, out of Towanda, PA. They provided some of the powders. It was mainly, they supported us in terms of material goods. And that we actually continued on. We are late getting all this work done because we're having all this trouble with the consolidation. So we actually continued on our own dime quite a bit, trying to work on that process. And the last phase was the wet milled deagglomerated powder is what we did. So wasn't that much to transition. I mean, I think the stuff that Brian talked about is an important thing in terms of a screening method for looking at these alloys. Knowing what we should stay away from, and how helpful improving iron additions might be to keeping us on the right side in our alloy compositions. I'll talk a little bit later about, it's also guiding some work. We have a similar project going on with nanocrystalline materials with RDEC, which was very successful. It's a different process entirely in terms of making the materials, but actually did develop the adiabatic shear behavior and everything. But we're able to use, again, these kind of the guidance from the corrosion and the health issues in terms of alloy selection for those materials. The GMP process itself was further improved. Maybe Kirk can talk a little bit more about it, but it's a nice technique for producing very clean, very fine grain-sized powders. Certainly we didn't have that before. In general, ARL has relied on nano powders that we obtained from China. So it was very good to have another source of supply and a process in-house so we could look at some of these materials. And the Chinese stuff was usually very high in oxygen, so that was often a problem. Let's see. The next slide, conclusions and summary. I just mentioned this. I haven't shown any of that data. That program is classified. you want to see some of that data, we could probably arrange something to do that. We did about a little over a year into this project, we demonstrated in this other program that yes, nanocrystalline tungsten-based materials can exhibit the desired behavior, but it was done by a different means than this glycine nitrate or freeze-drying, even synthesis processes. It was a different technique. So we are still pursuing that.
And you did indicate that the work that you have done in terms of toxicology is applicable to that effort as well.
Definitely. Yep.
Okay.
Yep.
That's something to definitely, and if it hasn't been, it needs to be pointed out and specified that at least that work was something that is transitionable or did transition.
Yeah. I think I had it on the transition slide. Maybe I didn't say it that clearly, but yeah,
okay.
It's definitely guiding all our continuing work this way.
Okay.
And helping us in terms of alloy selection.
Right.
Is it also, Lee, though, is it also impacting your non-long rod type development work?
The toxicity screening stuff?
Yeah.
I mean, in general, it does. It affects all that stuff.
Right.
Yeah.
There are a lot of tungsten projectiles that, this is a specific one, but there's a lot of other projectiles, correct?
Well, we've used that, all of the health studies that I talked about, when they've been looking at health hazard assessments and toxicity clearances on some new alloys, where they've selected materials that were not examined by Lori Rozelle in her study or by Kalinich, and so I guess this let the toxicologists understand the problem a bit, and it's something that they cited in the HHAs.
So yeah, just finishing up the conclusion summary. So there was a demonstration of the basic approach, although we didn't do it with our process, but that does work. The GMP process was further matured during this project, and our problem was with consolidation. We still have a problem consolidating powders made by this technique.
Well, that's physics. You have to, if you're heating and putting pressure, your potential to increase grain size is going to increase.
Right.
Oh.
I don't know. I mean, I didn't write it in the final report because it's more a suspicion than anything. But I mean, again, the fact that with this process, we produce a more intimate mixture of the tungsten and the other alloying additions. We're probably aiding this the fusion process and grain growth process more so than the competing process, I'll say. We have been fairly successful with the other process in terms of getting to nearly full density and retaining fine grain size.
So I think we're going to conclude here, but just a comment, and the comment is really that I think that this project was more of an R&D project than a demonstration validation.
Right.
And that's just the way it worked out. There was a lot of things that had to be answered before you could get to the demonstration, and you never quite, although you did test one quarter-size rod out, you never really got to the point where you could do a full-blown demonstration and show that the technology was appropriate for
right.
scale
Yeah, we were planning to demonstrate it actually in like a GAU-8 projectile. Was going to be the full-scale demo, and we never got to that phase.
Right. So that's just the way it worked out, and that's. I'm glad we have a report on it. I'm glad that ultimately there is a transition of the toxicology data that maybe guides future work in the area.
Yep.
So.
Yeah. No, I think
okay.
it's certainly given a lot of clarity to the what the real issue is. With
And that whole idea of dissolution, I'm not sure if that's something that people have looked at before, but it certainly makes a lot of sense that if it just sits there and doesn't dissolve, then it's not going to do any harm.
Right.
What, of course, you have to look at, when you think about depleted uranium, I don't think I'm as concerned about a slug sitting in someone's body as I am of the particulates or gases of combustion that would be around the battlefield if you're walking around a lot of dead tanks and a lot of burnt uranium.
I don't know if Lee mentioned this, I was out for a minute, but the rats that were implanted with DU did better than the baseline that were implanted with tantalum. They're better than the negative control.
Right, yeah. And again, I mean, maybe that's not the mode of concern.
Right.
I think inhalation would be far worse than
yeah, that's
and
the only way you're going to get any
bedding.
kind of radiation doses by inhaling. And
right.
and the toxicity, you're going to get large.
Yeah.
It's lead. It's comparable to lead in terms of its toxicity that way.
But I think if I remember the Capstone, I'm not a good enough health physicist for this, but if I remember the Capstone work, I think it even showed the inhalation was not that bad because it was hard to get a fine particle. Is that right? Is that?
Yeah, there were some aerosols, but yeah, they didn't stay suspended very long.
Yes, right. So your comment about it's more dangerous to be on the battlefield than in the presence of the burning uranium, I think was one of the conclusions is that of the Capstone work.
Yeah. Yeah, it's more.
Okay, are there any other questions from anyone? Any other comments? Okay, well, thank you very much. I appreciate it.
Okay, thank you.